Hello everyone, I welcome all of you to my YouTube channel. So today we are going to discuss a few questions from CSIR Net Chemical Sciences from part B. So the first question. In the first question we have been given a starting material and a reagent sodium methoxide, and we have been asked to find the major product form in the following reaction. So this particular reaction appeared in CSIR Net June 2019. So how do we proceed to solve this question? See, the reagent given is sodium methoxide, right? So sodium methoxide is a weak base. The function of a base is to abstract a proton. So our job is to identify the most acidic proton that is likely to be abstracted by the base. See, in this carbon we have two hydrogen, this carbon we have two hydrogen, and in this carbon we have one hydrogen. So if we compare the hydrogen in each of the carbons, this hydrogen is highly acidic because we have two electron withdrawing groups attached to this carbon. Since this hydrogen is highly acidic, the methoxide ion will abstract the proton. So this electron pair will push to this carbon, and you can see the carbon will develop a negative charge. But this negative charge will be stabilized by the existence of these carbonyl groups. See, we have 1, 2, 3, 4, 5 atoms over which this negative charge can be spread over. So basically we can say that after the abstraction of the hydrogen atom or the proton, we have formed a enolate, right? So after the formation of the enolate, there are two possibilities in which this reaction can proceed. See, the first possibility is this enolate, which acts as a nucleophile, can attack this carbon of the carbonyl group and undergo either nucleophilic substitution reaction or nucleophilic addition reaction. So if it attacks this carbonyl carbon, we'll get the product something like this, right? So for nucleophilic substitution to occur, there has to be a very good leaving group, right? But you can see that this phenyl group is not a good leaving group. So the possibility of nucleophilic substitution is ruled out. And in order to undergo nucleophilic addition reaction, there has to be a source of proton for this oxygen ion to abstract, and so we can rule out that possibility as well. So the next possibility is the nucleophile can attack this carbon. Why? Because you see this carbon is attached to a methyl group. This methyl, tosyl, these are very good leaving groups. So if this enolate or the nucleophile attacks this carbon, so this methyl group can leave very easily. So after the leaving group has departed, we can see that there will be the formation of a 5-membered ring, right? So this is the most likely product that is to be formed. So the option 1 is correct in this case. Option 1 is correct, right? So next we have, which one of the following pairs has two magic numbers for closed nuclear shells? This question appeared in CSIR Net 2017. So we have been given four options: 8, 10, 10, 20, 50, 82, 82, 130. So how to solve the problem? So in order to solve the problem, we have to know what is a magic number. So the magic number is the nucleides with 2, 8, 20, 50 and 82 protons, or 2, 8, 20, 28, 50, 82 and 126 neutrons are exceptionally stable. See, in this nuclei helium 2, 4, we have number of protons equal to 2. In this nuclear oxygen 8, 16, we have number of protons equal to 8. In this nuclear calcium 20, 40, we have number of protons equal to 20. In this nuclear lead 82, 208, we have number of protons equal to 82. So these are highly stable, right? And they also satisfy the condition of the magic number, right? So these are exceptionally stable nucleides. Moreover, nucleides with even number of protons, that is 2, 8, 20, 82 number of protons or neutrons. So we can get the number of neutrons by subtracting the number of protons from the mass number. It is 4 minus 2, it will be equal to 2. 16 minus 8 will be equal to 8. 40 minus 20 will be equal to 20. And 208 minus 82 will be equal to 126 neutrons. These are also observed to be stable. So if you look at the options, the correct option will be 3, that is 50 and 82. Next, so we have been given to choose the isoelectronic pair among the following. So we have been given 4 organometallic complexes, and from this we have to choose the isoelectronic pair, right? So how to proceed? So first we have to count the number of electrons in each of the organometallic complexes using the neutral atom method, right? So how to count the electrons? So if we the electron count for each of the following using the neutral atom method is, see, in the first organometallic complex we have vanadium. So the vanadium is surrounded by 6 carbonyl ligands. So in the neutral atom method, first we consider number of d electrons. So vanadium has 3 d electrons, and along with the d electrons we also consider the number of s electrons. So we have number of d electrons is equal to 3, and for s electrons we have 2 more electrons. So 3 plus 2 is equal to, we have 5 electrons, and this vanadium is surrounded by 6 carbonyl ligands. So the carbonyl donates 2 electrons. In neutral atom method, carbonyl group generally donates 2 electrons. So we have 6 carbonyl ligands. So 6 into 2 we have 12 electrons. So 12 plus 5 electrons we have 70 electrons. So the next organometallic complex is of copper. So copper is D9, and if we, along with 9 electrons, if we consider the 2 s electrons, we have 11 electrons overall for copper. And then we have one cyclopentadienyl ligand. So the hapticity of cyclopentadienyl ligand is 5. So in neutral atom method, the cyclopentadienyl ligand will donate 5 electrons. So along with the cyclopentadienyl ligand, we have one more carbonyl ligand, and carbonyl ligand donates 2 electrons in neutral atom method. So we have a total of 18 electrons for this organometallic complex. The next organometallic complex is of cobalt. So cobalt is D7. So along with the 7 electrons, if we consider the s electrons, we have a total of 9 electrons for cobalt, and the cobalt is surrounded by 4 carbonyl ligands. So 4 into 2 electrons, so because carbonyl donates 2 electrons, so we have overall 4 carbonyl ligands. So 4 into 2 will be 8 electrons, and we have one negative charge, so one additional electron we have. So the overall electron count will be 18 electron. So the last complex is of iridium. So cobalt, rhodium and iridium, these fall in the same group. So the d electron count for iridium is 7, and again we have to consider the s electrons. So 7 plus 2 will be equal to 9 electrons. For chlorine or chloride ion will give 1 electron in a neutral atom method, and a carbonyl ligand will give 2 electrons. And then we have 2 triphenyl phosphine ligands. So one triphenyl phosphine ligand donates 2 electrons. So while we have 2 triphenyl phosphine ligands, so 2 into 2 will be 4 electrons. So the overall electron count will be 9 plus 1 10 plus 2 will be 12. So 12 plus 4 will be 16 electrons. So if we see the electron count, so the organometallic complex of copper and cobalt have the same number of electrons, that is 18 electrons. So the correct option will be B and C. So I hope you have enjoyed this session, and thanks for watching. Nice day.